Welcome to Lecture 8.3, Predator-Prey Models. In the previous lecture, we analyzed systems of ODEs that modeled two species that were competing for the same resource. Now we will turn our attention to systems of ODEs that model two species, one of them a predator and one of them a prey. As before, we will heavily rely on the technique of linearization near fixed points to analyze the models. Let's start with a simple example. This is a predator-prey equation, and you can see that because if you look at this first equation in x and you get rid of the y, you make it 0, you get exponential growth. So this represents the prey where you kill off its predator and the population is going to explode. Now the second equation, y, in y, if you kill off make x 0, kill off its food source, you get exponential decay. So here, the population will slowly die out. Okay, so the first thing to do here is to find the steady state solutions. So we can set both of these equal to 0 and solve for x and y. Or alternatively, we can use the null-Klein method. That's what we'll do right here. So to find the null-Kleins, start with the x null-Kleins. Remember that happens when x prime is 0. So x prime is 0 when either x is 0 or 1 minus 1/2 y is 0. So that's either x equals 0 or y equals 2. So x being 0 is this, y equaling 2 is that line. Next, the y null-Kleins. These happen when, by definition, when y prime is 0. Hope that looks like a y. And these happen when y is 0 or when this thing is 0. So multiply through by 4 and you get -3 plus x equals 0, so x equals 3. So either y equals 0 or x equals 3. So you either get a horizontal line or this thing right here at 3. So the steady states are the intersection of the null-Kleins. Those are when both x prime and y prime are 0. So one of them obviously is at 0, 0 when both species are extinct. Or you have this one 3, 2, which represents when they are coexisting. This is 0, 0. Okay, so next thing to do is to analyze the behavior of the phase of the system near these fixed points. And we'll do that by linearizing. So first let's linearize near 0, 0. So to linearize near the fixed point 0, 0. Now we don't need to change variables because we are in the neighborhood of 0, 0. So to do that, let's multiply this thing out and ignore the nonlinear terms. So like x times y, that's all we have, x times y and y times x. We don't have any x squareds or y squareds in here. So here we have x, oops, let me get my pen back, x prime y prime is, well, I think we can do this one in our head. So there's only an x term. So this is going to be 1, 0, 0, -3/4 times x, y. And then there's, of course, a nonlinear term. If you want to, we can write this out as minus 1/2 xy and 1/4 xy. This is what we will ignore if x and y are approximately 0. So the linearization is just this part, and we can read eigenvalues and eigenvectors right off the matrix because it is diagonal. So here, lambda 1 is 1, lambda 2 is minus 3/4, and V1 is 1, 0, and V2 is 0, 1, as is true with any diagonal matrix. So now we can sketch the phase portrait near 0, 0. So this is x and this is y. Then this first eigenvector, V1, that is going to be right here. And the arrows point outward because the eigenvalue is positive. And the other one, 0, 1, so this is V1, and V2 is up here, and the arrows point inward because the eigenvalue is negative. So you can tell we have a saddle here, so that the solutions will look like this, a curve like that. You've seen this before. So what that means is if we are in the neighborhood of this steady state, then the solutions look like this. And I really only care about the first quadrant, but just for completeness, I will fill it in like this. So we're not yet sure from here if this is going to bend and go out to infinity like this, or if it's going to spiral around this point or sink into it. So that's what we want to figure out next. And we can do that by linearizing at the next point. So let's now linearize at x star y star equals 3, 2. So to do this, we need to change variables. So we let p be x minus 3. So x minus, so we're going to subtract off the steady state value in the x direction and the y direction. And q is y minus 2. So here, solve for x because that's what we want to eliminate in here. So x is p plus 3, y is q plus 2, and obviously x prime is p prime, and y prime is q prime. Okay, now let's plug these things into here. So to start, what's going to happen? X prime is going to be p prime, x is going to be p plus 3, and then we're going to plug in a q plus 2 in for here. So let's do that. So let's see. We get p prime. You see that prime? There we go. P prime equals p plus 3 times 1 minus 1/2 q minus 1. Are you okay with that? I took 1/2 times q plus 2, and that's what I get here. And so what this is going to be is, well, I'll do that next. Q prime equals q plus 2 times negative 3/4 plus 1/4 times x, which is p plus 3. So that's 1/4 p plus 3/4. So let's 1/4 p plus 3/4. And let's simplify this. Now, very nicely, this 1 and this negative 1 cancels. So let's get rid of those. As does this negative 3/4 and this positive 3/4. So we can get rid of those as well. So this thing here, the first one is just 3 times negative 1/2 q, and then the nonlinear term is p times q. So this is minus 3/2 q, and since it's short, we'll just write plus pq. Oops, that's supposed to be a plus. Yeah, it still looks like 1. And now down here we have 2 times 1/4, that's 1/2 p plus 1/4 pq. So 1/2 p plus 1/4 p times q. So as we ignored these nonlinear terms, we are going to ignore those as well. So let's write this in matrix form. This is p prime q prime equals 0 minus 3/2, 1/2, and 0 times pq. And the eigenvalues, if you plug this into Wolfram alpha, are lambda 1 equals plus or minus root 3 over 2I. They are purely imaginary. So what does that tell us? So that is the problem case that I spoke of at the very end of last lecture. That means the phase space are going to be ellipses, but that was that borderline case where unfortunately that does not necessarily, or I should say stable ellipses. So that does not necessarily imply that, so the things are going to circulate around this steady state. And as we can see from here, most likely it's going to be in the counterclockwise direction. The linearized version says there'll be stable ellipses, but since that's just a very fine line of threshold, we don't know whether the actual phase space is going to have stable ellipses or inward or outward ellipses. Now that's important because if the ellipses go inward, that means this is a stable fixed point and the population will be slowly approaching this equilibrium. And if it's outward, then it's unstable. And things are going to blow up and you're going to have big swings in the population. The predators are going to have a high population, the prey will be endangered, and then vice versa. And then, of course, the other case is that they could actually really be stable ellipses, in which case the populations are going on natural cycles of highs and lows if you circle around like that. Okay, so let me actually write that down. This is the problem case. And so now our next question is, how do we figure out which of these three possibilities actually arises in the phase space of the nonlinear system? Although before I leave you, I want to say a little bit more about this linear system. Let's see what shape the ellipses look like. Like, are they long and are they short and long, or are they tall and skinny? So to do that, note that dq over dp, so that's going to be the slope, and think like dy over dx, but in the pq plane. I think dq dp, that's just q prime over p prime, which is 1/2 p over negative 3/2 q. So, well, I should say that's by the chain rule, so dq dt, technically, over dp dt. So this is 1/2 p over minus 3/2 q, which is minus p over 3q. So now let's set those equal, or let's look at these two and let's equate that, and let's multiply the 3q over here and the dp over here. And if we do that, we get p times dp plus 3q dq equals 0. So now if we integrate both sides, I'm going to write it like this. So if we integrate both sides, that's supposed to look like an integral, we get that p squared plus 3q squared is some constant of integration. So let's call that k. So this is the equation of an ellipse. And if you're not familiar with it, that's fine. It's an equation of ellipse with, since 3 is bigger than 1, the ellipses here are going to be skinny or short and long like this. So if we go back up to our phase space, we don't know quite whether we have ellipses that are spiraling inward or outward, but we know they are going to be like, they're going to be a little bit elongated like this. So continuing our example, let's go back to the actual system in X and Y. We're going to try to figure out whether these ellipses spiral inward, outward, or are stable. So what we can do is we can look at dy dx, just like we did before, which is by the chain rule, dy dt over dx dt, or just x prime over, or y prime over x prime. So that's this equation over that equation. So that is y times minus 3/4 plus 1/4 x over x times 1 minus 1/2 y. Okay, so now we can separate variables. We can put all the y's on this side, so multiply this bottom term over there and this top term down there. Put all the x's on the other side. So it's sort of like what we did when we first learned how to solve differential equations. So the left-hand side is 1 minus 1/2 y over y times dy, and the right-hand side is minus 3/4 plus 1/4 x over x times dx. And now we can integrate both sides. Yeah, you got to be careful here because you got these constants, and you should probably factor out like the minus 1/2 and the 1/4. And it's easy to be off by a constant if you remember when we separated variables. So I will actually skip the steps because it's elementary. And if you do this, you get 3/4 natural log of x plus natural log of y minus 1/2 y minus 1/4 x equals constant of integration c. Now you can't actually solve for x or y here explicitly, but you can plug it into your favorite computer package or graphing calculator, and you can check that this is indeed the equation of an ellipse that's centered at 2, 3, and it's short and wide like this. So here that this is x and this is y. So what that tells us is that our original system is indeed a stable ellipse. And maybe that's a bit surprising because I was expecting a stable ellipse, you have to lie right on that vertical line, and it's easy to be nudged off to the left or the right where the ellipses are either going inward or outward. So now we can update our face portrait. So here is x and here is y, and here is, let's call this 3, and let's say 2 is like there. So now what you have is, well, we already know that we have steady states at 0, 0 and at 3, 2, and we have curves on the y-axis go down to 0. So that means if the prey is killed off, then the predator is going to slowly die off. So we have curves that go this way, and then curves on the x-axis go outward. So if the predator is killed off, then the prey is going to increase in population. And so similarly, if you have a curve that's really close to the y-axis, it's going to do something like this, and it will, of course, eventually come back and wrap around and make a big ellipse. So similarly, we have these curves, and maybe what's going to happen as you get closer is it's going to look like this. I don't know how good I am at drawing this. Probably not that good. They're not going to be perfect ellipses because this is a nonlinear system, and the ellipses that when you linearize it, you get ellipses, but what you get is you get these stable curves that cycle around like this. So think about what that means. That means we don't know how fast this is going, but over time, so when you're up here, you have a lot of prey and not a lot of predators, and then so the predators eat all the prey, and then the population of the prey goes down and the predators go up. but then there's not enough prey, so you keep going, and the predators go, and the population of the predators go down, and then as a response, a little bit later, the prey doesn't get eaten as much, and so they increase in population, and you coexist in spirals like this. So of course, if you started at 3,2, you would stay at 3,2 forever, but most likely, at any given time, the predator-prey population is not at equilibrium, so you're going to get these stable cycles. Now, this, of course, is the phase portrait, so this is x versus y, but x and y are both functions of t, so you can also plot the component plots like we did before. So if this is t, and this is x and y, let's do this. Let's plot one of them in blue and one of them in red. I think I used red for x and blue for y. So what's going to happen as you go around an ellipse, just focus on the x value. So ignore the y value. What's happening is you're going back and forth, back and forth. So let's see how I can draw this. So you're going to be cycling something like this. It's going to be sine or cosine-ish, but it's of course nonlinear. And then the y values are going to be are also going to be up and down. In this case, they're not going to vary as much because the ellipse is longer than it is tall. So there's going to be some sort of offset, something like this. I don't quite know what the offset is, but it's going to be like this, and so these are the actual functions x and y of t. So this is the let me write this down. This is the phase space, or the phase portrait, and these are the component. How do you spell component? P-O-N-E, and component plots. Our last example is a predator-prey equation where the prey grows logistically without the predator. So for this, let's solve it in terms of all of these constants, and then we will do an example where the constants are back in. So m is the carrying capacity of the prey, and just to make things easier, let's normalize things and set m equal to 1. So let's set m equal to 1. So even if m is like 2 million, you can normalize it and just change the units. So if you do this, well, let's first find the steady state. There's going to be more than one steady state. So that's going to be the solution to the following system. So set x prime equal to 0. 0 is, so we have r times x times, well, let's see. So there's an x in all of these terms. So let's factor out an x first, and then let's write what we have left, and we have r times 1 minus x minus s times y. And then the second equation, y prime being 0. So set this equal to 0, that's quite easy. It's just what we have it right there, y times minus u plus vx. Okay, so you can solve this one of a number of ways. How about if I just tell you what the solutions are, and then we will go over it with the null-clines. Actually, no, let's do it the other way around. Let's do the null-clines first. So the x null-clines, so this is when x prime equals 0. So this happens either when x is 0 or when this equation is 0. So this happens when x equals 0 or when r times 1 minus x minus sy equals 0. So what you have here is you have x equals 0 is just a vertical line, and this thing is going to be a line with negative slope. So it's going to look something like this, and then the hash marks, if x prime is 0, are going to be vertical. And if we are up here, then x prime is less than 0. So let's write that. So x prime is less than 0. So solution curves go this way. And if we are down here, then x prime is positive. So x prime is positive, and solutions go that way. Now let's do the y null clients. The y null clients. So this happens when, oops, let's fix that, when y prime is 0. So either y is 0, or this is 0. So or negative u plus vx equals 0. And this is a vertical line. So it's x equals u over v. So the y null client, or the non-trivial y null client, is going to look like this. And so there's going to be hash marks on it that are going to be horizontal because the y value is not changing. And it's easy to check that when you are to the right of this, y prime is positive. So in other words, if x is greater than u over v, then this is positive. So, or this part is positive. So y times that is positive. Positive times positive is positive, which means that solutions will go, oops, let me get my pen back, upwards. And to the left, we have y prime is negative, so solutions go downward. Okay, so let's plot this now on the xy plane. So here we have, there's the y-axis, here is the x-axis. We don't know what the values are, and that's fine. So the x null clients, one of them is x equals 0. That is a vertical line. And the other one is this thing here, which is going to be, it's just basic algebra to check that this is a line where the intersection here is going to be, the y-intercept is r over s, and then down here this x-intercept is going to be 1. And that's, again, if y is 0, not again, but obviously if y is 0, then x has to be 1 for this to be 0. So let's fill in these little hash marks. So along all of these x null clients, we have vertical little bars. You can't really see them here, but that's fine. And now the y null clients are y equals 0. So that's here. And the other y null client is this equation, which is x equals u over v. So that's going to happen somewhere like here. And so now you have hash marks that look like this. And now, oh, and also along here as well. So solution curves can clearly never cross the x or the y axis because they'll be going against the grain, and that's the way it should be. You can't have a population ever get negative. Okay, so the steady states are the intersection of the red lines and the blue lines, and that's easier than actually solving this thing explicitly, which is not that bad either. But it's a little more gentler. So there is one steady state, and the other one is down here. Actually, there's a third one right here. So it turns out that the steady states are, let's see, how do I want to arrange this? So this, let's do this. X star and y star equals, well, 0, 0 obviously is one of them. And then 1, 0 is one of them. That corresponds to when we kill off the predator and the prey reaches its natural carrying capacity, which normally would be m, but we're just calling it 1 for now. And then the third one is where they both coexist. So let me say or And it's not hard to, well, let's see. The x value of that is going to be, so this here is u over v. So the x value is u over v. And then what's the y value? Well, the y value is, it's going to be, well, just take the equation of this line and plug in u over v in for x and solve for y. And so you get r over s times 1 minus u over v. So that's r over s times 1 minus u over v. So these are the three steady states right there. Now what can we say about them? So let's first start with an application. Well, actually, before I do that, so these arrows, if we are above, or here's the x isocline, so if we're above this over here, then the solution curves go to the left, and if we're below it, they go to the right. And here's the y nullcline or isocline. If the solutions are to the left of that, they go down, and to the right of it, they go up. So we know that we're going to get this spiraling behavior like we did before. And indeed, if you linearize at 0, you will get that the solutions go down this way and over that way, which makes sense. The predator will die out if you kill off the prey, and the prey will converge to the steady state, or the logistic value. It's equilibrium if you kill off the predator. Now, if you have both of them, there's going to be some spiraling business, but it's not clear, again, whether it's going to spiral inward or outward or stable. So I'll get to that next, and actually, that's really hard to see for just if you're using value, what do I want to call them? Constants like r, s, and u and v. It depends on the values of r, s, u, and v. There will be values where it spirals inwards, and there are values where it spirals outwards, and I'm sure you can pick a value where it's stable. So we'll do that in the next example. But for now, the last thing I want to say is I want to give you an example of this. Let's suppose that x of t is a crop. And let's suppose that y of t is a pest or a weed. Let's say it's a pest. So this is an example of a predator-prey. We don't usually think of predator-prey as being a agricultural example, but hey, I'm at Clemson, and that's an ag school, so this is a good example. So if you have a crop and a pest, there is a natural equilibrium right here, and a farmer might think that a way to fight off the pest is to try to outgrow it. So plant a superior cultivar that has a higher growth rate, and the growth rate is going to be this this r right here, to attempt to outgrow the pest. That makes sense, right? Just outgrow it. However, what happens if you do that? So let me write that out. What happens if we increase r and nothing else? So we have a better crop. Well, in this phase space, this blue line, the y nullcline, has nothing to do with r. The only way that r actually appears is up here. So it's in this y-intercept. So if you increase r, then this is going to go upwards, and what's going to happen instead is this line is going to go up here. It's going to get steeper, and there will be a new steady state. This old steady state is going to go up, and it's going to go right there. So we get a new steady state. So what does that mean? Well, the new steady state has the same value of x. So the crop doesn't increase at all. However, the pest increases. So if the farmer tries to do this, they're going to get the same amount of yield from the crop, but they're going to get a lot more aphids, or whatever pest this is. So this is perhaps surprising. You think that you could outgrow a pest, or at least somewhat, but if this is indeed a reasonable model, this tells the farmer that it would be a complete waste of money to try to outgrow this pest. So you got to try something else. So I will conclude with an explicit example of we saw in the previous slide, where I've given values to R, S, U, and V. Now, again, we have formulas for the steady states, so it's not hard to see. If we plug those in, you actually get X star, Y star. You get steady states of, well, 0, 0. You always get that. 1, 0, that doesn't depend on the constants. And then you actually get 0.4375 and 1.4625. So those are the three steady states. And let's linearize at this third steady state. So to do that, we change variables, and it's going to be messy, so I'll just tell you what the actual algebra is. So you get P is X minus the X star, so that's P minus 0.4375, and Q equals Y minus 1.4625. And so this we solve for X because that's what we want to eliminate. X is P plus 0.4375, and Y is Q plus 1.4625. So if we plug these things into this equation here, and we simplify, so we plug in, again, I'm going to skip the algebra, but it's simple. It's P prime equals 0.5688 P minus 0.2188. I'm just keeping 4 sig figs. Q minus 1.3 P squared minus 0.5 P Q. And then Q prime is 2.34 P plus 1.6 P Q. So if you linearize this, you get that, let's see, you get P prime Q prime, P prime, I almost made that a fraction, P prime Q prime equals 0.5688, 2.34, negative 0.2188, and 0 times PQ, plus, again, plus nonlinear, NL. So if you compute the eigenvalues of this, you get that lambda 1 and 2, they're complex, and you get negative 0.2844 plus or minus 0.6565I. So these are the eigenvalues, and the thing to notice is that the imaginary part is 0. So that means we have inward spirals. So let's plot the face portrait now, and well, something like this, you can actually plug it into computer algebra or just computer software, something like MATLAB or Wolfram Alpha, and you can actually plot what this looks like. Because other than that, you're not going to be able to do it explicitly. Although you do know that there are inward spirals. So let's say what we do know explicitly. So we know that there are 3 steady states. Let's see. So we know that there is an x nullcline here, and there's an x nullcline here, and that is 1. And we know that there's a y nullcline here. Now my drawing is not going to be to scale because that is supposed to be 1.4625, and this down here is supposed to be 0.4375. So we have 3 steady states, one at 0, one at 1, and one right here. And we know that, as before, solutions are going to go toward the origin down here. The predator dies off without the prey, away from the origin here. And now we know that they are going to spiral, but they are going to spiral inward. So So we're going to get something like this. And so in this example, the populations are going to oscillate, but then they're going to level off, and they will approach the steady state solution. So over time, it's going to look like the predator and the prey are not going to be changing. And now if you plot the phase portrait, so suppose this is t, well then the x value, let's see, there's going to be, so this is going to be 0.4375, and let's draw these, let's write these out. So no matter where you start here, the x value is going to approach 0.4375, so that means that you're going to get some spiraling behavior, and it's going to go like that. And then the y value, the population of the predator, is going to approach this steady state right here. So this is going to be x of t, and this is going to be y of t. And again, don't try to worry too much about units, because we've already normalized and said that the equilibrium, the carrying capacity of x is 1. So this is what's going to happen. These are the component plots. Let me write that down. These are the component plots. And these over here, this is the phase portrait, or the phase space. Let's say phase portrait.